Welcome, data engineers. Let's get started on mastering the heart of Apache Airflow, working with DGs. Welcome, everyone. Today we are diving into the core of Apache Airflow, the DG. What exactly is a DG? It stands for Directed Acyclic Graph, and in Airflow, it represents your entire data pipeline. Let's break that down. Directed means there is a clear, one-way flow of execution from one task to the next. Acyclic means there are absolutely no cycles or loops. A task cannot depend on itself, nor can it depend on a downstream task. If you create a loop, Airflow will throw an error. In this graph structure, the nodes are your individual tasks, and the directed edges, the arrows connecting them, are your dependencies. Looking at this flowchart, you can see the three pillars of a DG. It splits into directed, acyclic, and graph. Notice how directed leads to a clear execution flow, acyclic enforces that there are no loops, and graph reminds us that our tasks are the nodes and our dependencies are the edges. This structural guarantee is what makes Airflow pipelines so incredibly stable and predictable. Why has Airflow become the industry standard for data engineering? Because it allows us to define ETL and ELT pipelines as pure Python code. Airflow DGs are entirely tool agnostic. Whether you are extracting data from an API, transforming it in Snowflake, or loading it into AWS S3, Airflow handles the orchestration flawlessly. Because DGs are just Python code, they're incredibly dynamic. They can generate tasks at runtime based on changing inputs. Furthermore, Airflow is highly scalable. Given enough compute, a DG can handle an infinite number of tasks. Finally, the Airflow UI visually maps out these DGs, giving your team instant visibility into complex workflows, drastically reducing the time it takes to troubleshoot pipeline failures. This diagram highlights the core benefits of Airflow DGs. From the center, we branch out to tool agnostic, allowing you to orchestrate anything. Moving down, dynamic and Pythonic design means your pipeline adapts at runtime. It's highly scalable for massive workloads and offers visual monitoring, so you always know exactly where your data is in the pipeline. It is the ultimate control center for data engineers. When creating a DG, there are a few critical parameters you must configure. First is the DAG ID. Every single DG in your Airflow environment must have a strictly unique identifier, otherwise, you'll experience unpredictable behaviors. Next is the start date, which tells Airflow exactly when this pipeline should start being scheduled. We pair this with the schedule interval, which defines the frequency of your runs, like running every 15 minutes or daily, using standard Unix cron expressions. Now, for a critical deep dive, the catch-up parameter. By default, if your start date was a year ago, Airflow will try to run every single missed interval up to today. To prevent overwhelming your cluster with hundreds of concurrent runs, you should explicitly set catch-up to false. Let's review the anatomy of a DG object. As you see in the chart, the DG object requires a unique DAG ID, a start date, and a schedule interval to determine when and how often it runs. Look at the catch-up node on the right. The dotted line highlights a major best practice: actively set catch-up to false unless you explicitly need to backfill historical data. This single setting saves many beginners from accidentally crashing their databases. How do we actually write a DG? Since DGs are just Python scripts, Airflow offers two primary syntaxes, traditional and the TaskFlow API. The traditional syntax uses a Python context manager written as with DG as DAG. Any task you instantiate inside this block is automatically assigned to the DG. However, Airflow 2.0 introduced the modern TaskFlow API. By simply placing an @DAG decorator above a Python function, Airflow registers it as a DG. The TaskFlow API is highly recommended because it drastically reduces boilerplate code. Instead of manually pushing and pulling data, TaskFlow automatically passes data between Python functions and infers the execution dependencies for you. You can freely mix both syntaxes in the same script, giving you ultimate flexibility. This flow visually separates our two writing styles. On the top path, the traditional syntax relies on the standard Python context manager. On the bottom path, the TaskFlow API uses the clean @DAG decorator. Notice how the TaskFlow path extends to auto-infers XCOMs and dependencies. This represents the underlying engine automatically wiring your data pipeline together just by looking at your Python function return values. Inside your DG, you need to execute work. That work is done by tasks and operators. Think of an operator as a pre-built blueprint or template. When you configure that template and add it to your DG, it becomes a task. Airflow has hundreds of operators built in. You can use the bash operator to execute shell scripts or the Python operator to run Python functions. If you are using the TaskFlow API, you simply put a task decorator over your Python function, and it instantly becomes a task. As a data engineer, leveraging these operators abstracts away massive amounts of complex connection logic. Instead of writing API connection wrappers manually, you just use an existing operator like the Snowflake or Postgres operator, pass it your SQL, and Airflow handles the rest. Here we see how a single Airflow task can be implemented in various ways depending on your needs. The implementation forks into 3 common paths: the bash operator for infrastructure scripts, the Python operator for classic Python execution, and the highly modern task decorator for clean, native TaskFlow Python execution. You simply pick the right tool for the job. Creating tasks is only half the battle. We must define the order in which they execute. We do this by setting up dependencies. In the traditional syntax, Airflow cleverly uses Python's bit-shift operators. The right bit-shift operator means set downstream. So, task A, task B guarantees that task A must successfully finish before task B begins. The left bit-shift means set upstream. To run tasks in parallel, you simply place them inside a Python list. For instance, task A, task B, task C means after A finishes, B and C will trigger simultaneously. For a deep dive, when you are building massive enterprise pipelines, constantly chaining bit-shift operators becomes messy. Instead, you can use Airflow's built-in chain, or chain linear, functions, which map out complex, multi-branch dependencies in a clean, readable format. Let's trace this dependency graph. Task 1 acts as the starting node. Using the right bit-shift operator, we branch out to task 2 and task 3, simultaneously representing a list dependency. Once both parallel transformations complete successfully, they converge back downstream into task 4 for the final load. This visual is exactly how Airflow's DAG engine interprets your bit-shift code. Let's tie all of these concepts into a highly critical, real-time use case, a data quality ETL pipeline. Imagine we are ingesting weather API data into Snowflake daily. We first load this data into a temporary staging table. But before moving it to production, we must ensure it is accurate. We implement Airflow's built-in SQL column check operator and SQL table check operator. We write assertions verifying there are no null values in our IDs and that our daily row count is greater than 0. If the data is corrupt, the SQL operator fails fast, halting the pipeline to protect our production tables. But we don't just let it fail silently. We leverage Airflow's on-failure callback on the DG, which instantly triggers a Slack webhook operator. This sends an automated Slack message to our data engineering channel with the exact context of the failure, enabling rapid response and preventing bad data from corrupting our executive dashboards. Look at our production architecture here. Data flows from our ingest task into the critical decision node, SQL quality checks. If the data is pristine, we follow the pass path, loading into production and cleaning up our staging resources. But if the data is corrupt, we hit the fail branch. The pipeline immediately halts, stopping downstream corruption, and fires a Slack webhook alert so your team can investigate instantly. To conclude our training, you absolutely must follow these senior-level best practices. Rule number 1, avoid top-level code. Airflow's scheduler parses your DG files every few seconds. If you place a heavy API call outside of an actual task definition, you will crash the scheduler. Rule number 2, implement incremental loading. Use Airflow's built-in Jinja template variables, like data interval start, to strictly process only the past 24 hours of data rather than scanning your whole database. Rule number 3, idempotency. Always design your tasks so that if a DAG fails halfway through and you rerun it, it does not duplicate your data. Thank you so much for joining me in mastering Airflow DGs. Please invite your colleagues to like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. See you in the next session. This final chart serves as your ultimate pipeline checklist. By maintaining clean top-level code, injecting Jinja variables for incremental processing, and strictly enforcing idempotent design, all paths lead to one clear outcome: highly optimized, robust, and scalable Airflow DGs. Memorize this chart, and you'll be coding like a senior data engineer in no time.